We learned about potential energy yesterday. We learned that there's several kinds of potential energy, only one of which we talk about for now in Physics 20, one of which we talk about a little bit later on, maybe about a month in Physics 20, and then a couple others that we talk about in Physics 30. The first kind that we do talk about today, in fact, in Physics 20, is gravitational potential energy. Gravitational potential energy is the energy stored. That's what potential energy is, right? Energy that's stored, energy that has the ability to do work but isn't doing work right now. It's the energy stored in an object due to its height. The higher the object is, the more potential it has to do work. Now, the other kind that we'll deal with in Physics 20 but aren't dealing with for another month is spring or elastic potential. This is, I think, the kind that Parker was talking about yesterday. It is the energy that's stored in a stretched or compressed spring or elastic, or something that's like a spring or elastic. Okay? If I bounce a basketball on the floor, that basketball squishes. As it squishes, it converts kinetic energy to elastic potential energy, which is what propels the ball upwards when it's released, right? When the ball goes back to its normal shape. Spring or elastic potential energy. 1 second, Henry. Another kind of energy that we don't talk about in Physics 20, but we do talk about in Physics 30 is nuclear. The energy stored in the nucleus of an atom. If we could somehow harness that, then it can do work. It can move things. It can become kinetic energy. So it's potential that can become kinetic energy. We also talk about electric potential energy in Physics 30 as well. The energy that's required to get an electron moving through an electric circuit or across some kind of gap. And finally, we talk about chemical energy as well, not in physics so much, but we talk about chemical potential energy in chemistry class. Chemical potential energy is the energy that's stored in chemicals. Okay, it's the energy that propels us forward. When I make a decision to start walking, it's chemical potential energy that allows me to walk. And when I push my foot on the gas pedal of my car, it's chemical potential energy of the gasoline burning in the engine that causes the engine to propel the car forward. Andy, you had a question? Is what, sorry? Vacuum potential energy? Not that I've ever heard of. Yeah. That's a good question. Yeah, that would be, there's a pressure differential there. I don't think you wouldn't call that like a vacuum potential or anything like that, but yeah, that's a good question. There's a pressure differential there, but I'm not sure that it's almost like there should be a type of potential energy there, right? But I'm not sure what you'd call that though, if you did. Yeah, good question. Yes. Yeah, Ethan? No, not at all. If someone was a paraplegic, they don't lack the potential energy required to do it. It's just that potential energy can't be harnessed to do it. It would be like, it's almost analogous to saying, you have a rock on the 100th floor of a building on a balcony, but they put a net. There's a net right over the edge. So you push that rock over the edge. It has the potential to fall to the ground, but it can't fall to the ground because there's something that's keeping it from falling to the ground. So that would be the same thing. That would be the similar type thing there. If someone was a paraplegic, they have the chemical potential energy in their body to make things work. They just don't have the ability to transfer the signal from their brain to use that energy to make it work. Does that make sense? Now, this is the kind we're focusing on, of course, in Physics 20. And the equation that represents gravitational potential energy is EP is equal to m times g times h. M stands for mass. It's measured in kilograms. G stands for gravity. It's 9.81 meters per second squared, although we put a little star by that one because gravity can be different, right? Depending upon where you are on Earth, depending upon, if you happen to go to the moon, then on the moon, gravity is 1.6, so your potential energy on the moon would be m times 1.6 times h. H is the height, okay, and the height is going to be measured in meters. EP is the gravitational potential energy. It's measured in joules, and it's going to be a scalar. All types of energy are scalars. There's no direction ever associated with any type of energy. Yes? All right. Let's take a look at example number 3 here now for potential energy. It says a 0.75 kilogram rock sits on the railing of your back deck. The railing of the deck is 1 meter above the deck, and the deck itself is 1.3 meters above the ground. Calculate the gravitational potential energy of the rock relative to the deck and relative to the ground. Remember we said yesterday, the gravitational potential energy is always measured relative to really whatever you want. The potential energy of this board marker right now relative to the ground is something, because it has potential to fall to the ground. But relative to my hand, it's 0. It has no potential to fall to my hand, because the height relative to my hand is 0, and the height relative to the ground is something. We're going to define the potential energy question A relative to the deck, and in question B, we're going to define it relative to the ground. So in both cases, we're going to use the equation EP is equal to mgh, the one that we learned yesterday and the one that we just reviewed a minute ago. The mass, of course, is 0.75 for both of them. G is 9.81, assuming you're somewhere on Earth where gravity is more or less average. And the height, what's the height that we're going to use in the first question here? Yeah, Aoife? No, not 1.3. Luke? Yeah, it's 1 meter. The rock is 1 meter above the deck. If we want to find the potential energy relative to the deck, we're going to use the height above the deck. Does that make sense? So we're going to say for this one, 0.75 times 9.81 times 1 is 7.3575, or we'll say 7.4 joules. Now, would you expect the potential energy relative to the ground to be less than, greater than, or equal to the energy relative to the deck? Yeah? Yeah. It has more potential to fall to the ground than it does to the deck, right? Because it's higher relative to the ground. So let's say EP is equal to mgh for that one. M is the same, 0.75. G is 9.81. And H, I should say. H is going to be what in this case? Yeah, it's going to be 2.3, not 1.3. We're not on the deck. We're on the railing of the deck, which is not 1.3 meters above the ground, but rather 2.3 meters above the ground. Unless the question specifies like this, you can define your ground level or your bottom level wherever you want, the deck or the ground. Okay, but if you're defining it relative to the ground like we are in question B, make sure you include the total distance from where it is to the ground. So it's going to be 0.75 times 9.81 times 2.3 gives me a value of 16.9, or we're going to round that to 17 joules. That make sense? All right, what I'd like you to do now is work on worksheet number 17, which is the back side of that sheet that I gave you yesterday. There's 4 questions on that sheet on potential energy. Let's go through each of these questions. We won't solve all 4 of these questions, but we'll at least go through the method that we would use to solve all 4 of these questions. Number 1 says, how much gravitational potential energy does this book have relative to the ground? If it's on the table, that it's that's 1.3 meters above the ground. We're just simply going to say for this one, EP is equal to mgh, and the height that we have here is 1.3 meters. That's the height that we're going to use. We're on the table. We want to find the potential energy relative to the ground. We use 1.3 meters. Now, if we wanted to find the potential energy relative to the table, it would be what? If we're on the table, how much potential energy do we have relative to the table? 0, because the height would be 0 in that case. 2, what's the height of the same 2 kilogram book if it has 42 joules of potential energy? For this one, we're just going to rearrange. Mg goes over by dividing. Look at this equation. If we're trying to solve for H, we're not going to say mg over EP. We're taking mg by dividing, so it's going to be EP over mg. So what is it, 42 divided by 19.62? Going to be somewhere 2 point something, 2.1, 2.2, something like that for the height. Here we have to watch out for the units. We're going to say EP is equal to mgh for this one, but be careful, m is 0.035 kilograms. Got to convert that from grams to kilograms, but divided by 1,000. 9.81, and the height here is 1.35 meters. So whatever that works out to be is our potential energy there. And finally, question number 4 says a 0.75 kilogram book sits on a box, sits on a table, what's the potential energy of the book relative to the table? For this one, we're going to use a height of, what's our height going to be for this one? The book is on a box. The box is on a table. What height do we use? 0.3. Good. 0.35. And we want to find the potential energy relative to the floor. What height do we use for this one? We're on a box that's 0.35 meters high. The table is 0.95 meters high. 1.30 meters is what we use there. Does that stuff make sense? All right.